So we are going to continue to discuss the breeze first search and especially the code part. So this function cal BFS, we take two parameters. One is a G and G is a graph, right? So for the G we have the E, which is a set of the edges, and we have the V, that is a set of the vertices. And remember, we also need the second parameter S, and S will be the start point of the search, or the root of the search tree. So remember, the ultimate goal is, when we do the breeze first search, we want to explore the graph, and also we want to build a tree structure based on the graph, right? So S will be the root. And the first step, we have to do a iteration. So we have to visit each of the vertex, and we color that as white, and then we do the du, so as infinity, and the pi u as new. So what do they mean? So for the pi, it means the parent in the tree structure. So for each of the node, as long as it is not a root, it should have a parent, right? And for the d, it is the distance to the root. So if the current node itself is a root, and then the distance to the root is 0, or if the current node is the direct parent, a direct child of the root, and then the distance should be 1. Okay, so for this iteration, we just initialize the vertices. And the next step, we want to touch the root. So for the root, we color that as gray. And what does gray mean? Gray means we have already discovered that node, but we haven't fully explored that yet, right? And then for the ds, so the ds is the distance to the root. Since s itself is a root, so the ds will be a 0. And then for the pi s, that is the parent of the root. And s itself is already the root, so it will be a nil. And then we initialize a q. So the q data type, that is the first in, first out, right? So first in, first out, that's a q. And we enqueue the s, so we send the s, the root, into the queue. Okay, and the next part, we start another iteration starting from the line 10. So as long as the queue is not empty, and then we dequeue one of the node. We dequeue the node, and then we touch the children. So we touch the adjacent nodes here in the for loop, and eventually we want to color that black. So what it does is we dequeue one node, and then based on the current node, and then we have to touch, or we have to explore all the adjacent nodes, and eventually we have to color that as black, saying we have already fully explored the current node. Okay, and how do we explore the adjacent nodes? So for each of the adjacent nodes, and then if the color of the adjacent node is white, and then we want to color that as gray. And then for the new node v, the distance to the root will be the du plus 1, and then the u will be the v's parent, and then we also put that v into the queue. Okay, so the code itself is dry enough, and probably you didn't enjoy too much. And let's see an example. So for this example, this is the setup of this graph. Okay, so we have already done the first iteration, which is, the color, we color all the nodes to white, and then for the du is infinity, and for pi u, that is, they are all nils. Okay, so that's the first step, and we want to start from the s. So for the first step, s is the root, so we color the root to be gray, and then we send s to the queue. Okay, and this is the first iteration. And after that, we have to iterate through the queue. So for each of the rounds, we want to touch the node, and we touch the node at the head of the queue. And then for the adjacent nodes, we want to color both of them to gray. And then, we are using the red line to show the pi. So for example, for the w is going to be is going to be the direct child of the root s. So we are using the red line saying for the w, the parent of the w is s, and for the r, the parent is s as well. And for now, we have touched or we have explored the root s, and then we have dqs, and then color that to be black, and we have nq, w, and r, right? So the next one we want to dq another value, and that should be the head of the q, which is w. And after that, after we dqw, and we also explore the adjacent nodes, and which are t and x. So for both t and x, well, we have colored this line to be red and this line to be red. The reason is, well, t's parent will be w and x parent will be w again in the tree structure. And now w is fully explored. We have nqt and x. And now the next node we are going to explore will be r, because r is the head of the queue. Okay, so if you want to explore the r, and then we find another node v. So v is inqueued, and then r is colored to be red. And at the next step, we have to see the head of the queue again, that is the t. So for the t, well, we are only exploring the white node, so we are going to explore u. Okay, so the next one, t is black, and then we explore the u, and u's parent will be t, and u is in q now. And the next step, we have to visit the x. So for the x, we will find another white node, which is y. So we paint x into black, and then we find y, and now y is gray. And the next step, the head of the queue is a v. So for the v, there's no more adjacent white nodes. So what we have to do is we just paint that into black, and that's it. And for the u, we want to find more white nodes, and there's no more white nodes, so we stop there. And for the u and for the y, they are the same, so we just color both of them to black because there's no more white node to explore. Okay, so eventually now our queue is empty, and then since the queue is empty, well, we can say, okay, we have finished exploring the graph, and we have also used the red lines or the pies to show what are the parents to each of the nodes. So now we also have a tree structure. So if we consider S as the root, and then S has two children, R and W, right? So R has V, and W has T and X as two children, and T has U as a child, and X has Y as a child. So this is already a tree structure, even though it doesn't really look like a tree structure. Okay, so before we finish, let me show you this visualization I made. So we started from the upper left. So we initialize all the nodes, and then we have the infinities, and then all the edges are not in the red color, and we ended here on the lower left. So this is after we have fully explored the image. And remember, for the D, it means the distance between each of the node to the root, right? So S is, so for the S is the root. So for the DS, it is a 0 because S itself is the root. And then for R and W are here. So R and W, they are the direct children of the S. So the distance to the distance from R and W to S will be 1. And then how about V? So V, the distance between V to the S will be a 2, because for the V, it has a parent of the R, and R has a parent of the to the S. So the distance between V to the S will be a 2, right? Okay, and how about the pi? So for the pi S will be a nil, saying it S itself is the root, right? And then for the R's parent is S, so pi R is the S, saying, well, R has the S as the parent. And then how about V? So pi V will be the R, because, well, if you see here, so it should be like this. So V's parent will be R, and R's parent should be S. So this is the final status of the D and the pi. And as we as we paint the nose and update the colors, and we also update the D and the pi. And this is the finished version of the D and pi after we finish the Breeze first search. Okay, so we are going to do a little bit more analysis of the algorithm, and I will see you in the next video.